Hey everybody, welcome back. It's been a while since I've recorded over Zoom at home. I wanted to hit you up with 9.1 and 9.2. We're going to do them as a couple of different videos though. This is Math 66. Oh, bad pin already. 9.1 is on sequences. I'm going to scratch that pin right now, grab another black. Hopefully this one's better. So what's a sequence? A sequence is a succession of objects following a pattern. Okay. So some examples, basic ones. We could do 2, 4, 6, 8, ... The pattern keeps going. We could do something like this. Ooh, purple, I like it. -2, 2, -2, 2, -2, 2. Or we can have something, even simpler. One, 1/2, 1/3, 1/4, 1/5, up to keep going to like 1/n. So generally we name or label these terms based on their position. This is the first term. Second term. And like nth term. And when we do that, it allows us to write it in a simplified notation. So I can take this first one, if I look at it, is really 1/1. So I can write this as well, 1/n, and n is going to go from 1 to infinity. This is a shorthand notation to indicate a sequence. Okay. We call this the brace notation because it uses braces. Did not know my phone was going to do that right now. Let's turn that off. So how can we do the other ones here? If this first one here is, these are all multiples of 2, right? +2, +2, +2. Repeated addition is multiplication. We can say that is 2 times n if we pick the right starting n. We want the first term where n equals 1 to be 2. And if I use 2n, that's going to work. So I can say 2n where n equals 1 to infinity. I've got something like -2 and 2. This one gave myself a little bit more room to work. This looks like 2 times -1 to the n, or maybe -1 to the n plus 1. I'm not sure which one it is alternating. These two are methods of alternating signs. So let's take a look and make sure we get the one that gives us the right one. If I want the first term to be negative, I need the outcome of this to be negative. If I put in n equals 1 here, -1 to the 1 is going to work. If I put in 1 here, -1 to the 2 is positive. That's not going to work. So the shorthand notation for this would be 2 times -1 to the n for n equals 1 to infinity. And if the sign started just the other way around, put up another sequence here. 3, -3, 3, -3, 3. This one would be 3 times -1. And we need the first term to be positive, and the n+1 term allows us to do that. Okay, so these are what sequences are. Pause the video if you need to keep writing notes. I'm going to keep flipping pages as necessary. Let's take a look at a couple examples and hit them from scratch. Just go through some reasoning. Let's say we have a sequence 2, 2/3, 2/9, 2/27, and we want to write it in brace notation. So a good way of doing it is setting it up and like writing down what n is below it. I want a color that pops. I'm going to use red. So that would be my first term, my second term, my third term, my fourth term. I need one for an nth term. That's what we're going for. What's going on here? The top doesn't really look like it's changing, does it? I could probably shorthand this as 2 over something, but what? Well, ignoring the first term, the denominator here, this one looks like 3 to the first power. This one looks like 3 to the second power. This one looks like 3 to the third power. If I wanted to apply this pattern to n equals 1, I could, if I said the denominator was 3 to the 0, because that would give me a 1, and 2 over 1 is just 2. And so once we've got a little sequence of going on with what's going on, now we can start lining stuff up and going, okay, n is 1 and this is 0, n is 2 as this is 1, n is 3 and this is 2. So maybe this one has like a, it's going to be some power of n. If you're not sure which one, try out a couple and see which one works for you. If I do n equals 0, this one, it gives me 3 to the -1. 3 to the -1 is 1/3. This one gives me 3 to the 0, which is 1. And this one gives me 3 to the 1, which is 3. The one I want here is, well, I don't want n equals 0 though, do I? I want to start with n equals 1. So if I had n equals 1, this is 3 to the 0. That'd be 1. N equals 1 here, 3 to the 1 is 3. And n equals 1 here, 3 to the 2 is 9. The one that's matching up, I don't know why I said n equals 0. Sometimes we start with 0. This is though, not generally. The one that matches up with what I want here is this one. N equals 1. I need the denominator to be 3 to the 0. So I'm going to put 3 to the n minus 1 in here and throw my curly braces on it. Why don't you guys try this next one? Pause the video and see what you come up with. All right, I will assume you paused it. I'm gonna throw some labeling below it. And I'm going to try to recognize a pattern. First off, I do see that it's alternating signs. So that means either -1 to the n or -1 to the n plus 1. I want the first term to be positive. And if I plug in 1, the one that gives me a positive 1 is going to be this one. So that's the first thing I know there's going to be a component. Then ignoring the negative signs, what's going on along the numerator and the denominator? I'm going to rewrite that as 1/1 so I can get a numerator and denominator feeling here. My numerator looks like it's going 1, 3, 5, 7 without the signs. So in each of these, I'm adding 2. So again, adding repeated addition is multiplication. I'm gonna, it looks like maybe some form of 2n. And if you're not sure what's gonna work, try 2n, 2n plus 1, and 2n minus 1. See what gives you a good feeling for what's working here. If I try n equals 1, let's do n equals 2. I want to make sure I get the right thing on bottom. If I plug in, not on bottom, on top, if I plug in n equals 2 here, I get 4. Here I get 2 times 2 plus 1 is 5. Here, 2 times 2 is 4 minus 1 is 3. That's the one I'm looking for there. And if I take a look at my denominator, it's going 1, 4, 7, 10. So this is repeatedly going up by 3. That's going to give me a multiple of 3n and then plus or minus 1 or so. We can try our test point, try how we can try n equals 3 here. By try n equals 3, that's a 9, that's a 10. That's, oh wait, I meant to write a minus 1 here. 8. And I am looking for on my third term. Well, I don't have the right value, do I? Maybe I need to try another one. What about 3n minus 2? 3n minus 2 is looking okay. 3 times 3 is 9 minus 2 is 7. Let's make it sure it works for another one. N equals 4. 3 times 4 minus 2 is 10. And that's what we want on our fourth term. So it's looking like that's the bottom that we want. So if I wrap this all up, I've got 2n minus 1 on top, 3n minus 2 on bottom, times -1 to the n plus 1. N equals 1 to infinity. Oh God, that's a terrible curly brace. God, that's terrible. I'm embarrassed. All right. Keep going with this. So a sequence is a function. And again, another dead black pen. Let's try another. The sequence is a function whose domain is the set of positive integers. So if we have like a sub n, where n equals 1 to infinity, this is like saying f of n equals a sub n, where n is 1, 2, 3, onward like that. And we use a sub n. I used this earlier, and I don't know if you know the notation. We use this to describe the nth term. So like a sub 0, if we had an a sub 0, would be the 0th term. A sub 1 is the first term, etc. Let's take a look at an example. We saw earlier we had 1 over n equals 1 to infinity. So f of n equals 1 over n. And if I do like f of 1, I have 1 over 1, which is 1. F of 2 is 1/2. F of 3 is 1/3. And we could graph these. So n equals 1, we get a 1. So this is the n axis. And if I do n equals 2, I get 1/2. N equals 3 would be 1/3. N equals 4 is 1/4. N equals 5 is 1/5. And we're doing something like that. But it's not a line, it's just the points. Because this function does not take in non-integers. If we compare that to like f of x equals 1 over x, we're getting something like the whole line here. So that's f of x equals 1 over x. And we get the whole line. Obviously, maybe I shouldn't extend it past. I don't want to go too far. Let's just say x is greater than or equal to 1 here. And sometimes we are going to use this to figure shit out. Okay? We can't do some things with the dots that we can do with the full function. So sometimes we will, it's called extending the domain. We can extend the domain from n being positive integers to n greater than or equal to 1. Okay. All right. So what more do we have going on? Limits. Let's talk about limits. We're going to have limits of sequences. And what is really going on here is what we're asking is what is happening to the nth term. As n gets really large. I.e. as n goes to infinity. Well, if we look at our last example, where we had 1 over n equals 1 to infinity, this is 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over k, I'll use a different letter. Eventually, as n goes to infinity, we're getting up to like 1 over infinity. If we could write that, that's not even a legal thing to write, but that's going to 0. So 1 over infinity is 0. So this is the limit of n going to infinity of 1 over n equals 1 to infinity is 0 kind of thing. Then I probably don't even want to write it that way. Let's just write it limit as n goes to infinity of 1 over n. And I don't need the curly brace. And this, because it's kind of implied. Okay? Because that's what we do with n's. N is done that way. So I don't know if you guys have seen the delta epsilon proof before for limit notation, but like the definition, the actual definition is a sequence converges to L if there exists an epsilon greater than 0. And there also exists, the notation for there exists is that, a backwards capital E. There also exists an integer n. Let's use big N, such that the absolute value of a sub n minus L is less than epsilon for n greater than big N. And what that boils down to is limit as n goes to infinity of a sub n equals L. Just to give you a little example of what we had up there, maybe we say epsilon is, comparing this to our previous thing, epsilon is 0.1, which is 1/10. So when n is greater than, I don't want greater than or equal to 10, but let's, because otherwise I'm not going to get it. Let's go 11. I have 1 over 11 minus 0 is 1 over 11, and that's less than my epsilon, which is 1 over 10. And so my big N would be 11 here to match this epsilon here. Probably don't want this. I'm going to get rid of this. There exists there. I'll write the notation here. Looks a little awkward with it twice. So if epsilon is greater than 0, there exists an integer n such that this is going on here, which is really showing Our distance here, going back to this one, our limit is 0, which is the axis. So this distance right here is a sub n minus L. And if I put in absolute values, it doesn't change it. That's what's really going on there. And this is from next page. When I scan it, it's not going to make sense seeing the a sub n minus L there. But that's what's going on. While I'm talking about the definition here, a sequence that doesn't converge is divergent. Or diverges. So that's a little subset of that idea. Our limit properties all apply. Just go through them real quick. Basic limits for sequences. If I've got sequences AN and BN, and this one converges to L1, and that one to L2. I can say, well, the limit as n goes to infinity of C is just still C. Limit as n goes to infinity of C times a sub n. Well, constants, C represents a constant here. That can get factored out of a limit. And this is just C times L1. As we saw, that converges to L1. We can add them. Limit of a, or n as n approaches infinity, we can add or subtract. Bn is either going to be L1 plus or L1 minus L2. So the limit can be separated over both of them. We've done that with our limits. If we have a product of them, limit as n goes to infinity of a sub n times b sub n. This just goes to the product of them. And obviously, this is the same thing as having division of the reciprocal. Or division is just multiplication of the reciprocal. So if I add a sub n over b sub n, we could do L1 over L2, given L2 does not equal 0. Or if. Basic limit stuff, they all still apply. So what about this one? Like pause and figure out what it is. Find the limit of 2n cubed minus 3n plus 6 over 4n cubed minus n as n goes from 1 to infinity. All right, if you hit that with the limit, one of the strategies we used in doing limits is to divide by the greatest power on bottom. This is not 0. So we can do this. And this turns into 2 minus 3 over n squared plus 6 over n cubed, all over 4 minus 1 over n squared. And as we apply the limit, that goes to 0, 0, 0, and we get 2/4 or 1/2. Okay, let's take a look at another one. Let's find out if this sequence converges. We're looking at n to the negative 4/3 over sine of 1 over n. So when you start off doing limits, you always try evaluating. Like this is 1 over n to the 4/3. So if I do limit as n goes to infinity of n to the negative 4/3 over sine of 1 over n, that's infinity on bottom, makes the top go to 0. This is going to sine of 0, which is 0. This is an indeterminate form. And L'Hopital would be great, but L'Hopital doesn't work for, just integers. It's designed for the whole number line. And so like it's not a line, so it's not differentiable. That's the idea. L'Hopital, we're taking derivatives, and the derivative, if there's no line, how are we doing a derivative? No line, no derivative. So what we're going to do is we can extend the domain to use all of x. To use the real numbers. And when we do something like this, we have n change to x. As x is our real number line, we use x and y. So we use n for integers, x for real numbers. So here now, when we look at this again with real numbers, we have the limit as x goes to infinity of x to the negative 4/3 over sine of 1 over x. This is 0 over 0, which triggers a L'Hopital event. If I take the derivative of the top, I've got negative 4/3 x to the negative 7/3. And here, this goes to cosine of 1 over x times the inside, derivative of the inside. Derivative of the inside would be, that's x to the negative 1, so that's negative 1 over x squared. And we're still doing limit as x goes to infinity. But we're not gonna, these two can mix. We can put these together because that is just like multiplied by x squared over x squared. X squared on top, X squared on bottom. So if we clean that up, I've got -4/3 X. If I move it to the top, I'm really adding these two exponents. So this is like -2 1/3 plus 2. That's going to give me a -1/3 there. And on bottom, I just have cosine of 1/x. As we do the evaluate the limit now, the top is still a negative exponent, which means 1 over like the cube root of x here. This is going to 1 over infinity is going to 0. 1 over infinity is going to 0 here, but cosine of 0 is 1. So the limit here is 0, which means the limit of the original sequence is 0. This converges to 0. Because it follows the exact, it basically, our end sequence is x, the f of x, but just at integer points. It's important to note, this doesn't always work. You can't do this for everything. Not all sequences can be converted to functions of x. Or can be extended to the real numbers. And f of x. For example, if we take n factorial from n equals 1 to infinity, if I try to do f of x equals x factorial, well, what about like f of 1/3? 1/3 factorial is undefined. We don't have anything for that. So it doesn't extend right. That is an exclamation point. And we're almost done with this video. And then I'll do 9.2 in a separate video. Let's take a look at another sequence here. Does the following sequence converge or diverge? Like -1/2 to -2/3, 3/2, -3/4, 4/3, -4/3, 5/4, -5/6, 6/5. And what I'm going to do is I'm going to graph these here. So this is like n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or our sequence. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to do the ones that are negative in red. So n equals 1 is -1/2. N equals 3 is negative 2/3, a little bit lower. N equals 5 is negative 3/4. That should be a negative 4/5 right there. Negative 4/5 for N equals 7. Let's see, that's 5. That's 10. So N equals 7 is here. Negative 5/6 for N equals 9. It looks like if I made an asymptote here, it looks like it's approaching negative 1 on bottom. And if I do the even ones, N equals 2 is 2. I need to go higher. And then N equals 4 is 3/2. N equals 6 is 4/3. 5/4. 6/5 is like 1.2. This looks like it's converging on 1. So approaching is the same thing as converging. So this diverges. This sequence is divergent. We do have a theorem that we can use that's kind of nice. And it makes sense coming from this picture. If the limit as n goes to infinity of the absolute value of a sub n equals 0, then limit as n goes to infinity of a sub n itself goes to 0. And this is based on the definition of absolute value. Absolute value of a sub n is a sub n if it's positive, and negative a sub n if it's negative or less than 0. So like we have like if I put, I'm gonna do it like this. If we do this, that's going to be true for any sequence. Like if a sub n is like 3, then this is negative 3, and a sub n is 3. That still meets the requirement there. But now we're going to look as n goes to infinity. I don't know if this definition really helps here. We got the, and I'll do the limit of everything. I'll pull the limit or the negative sign out there. Negative limit of n goes to infinity of a sub n is less than or equal to the limit as n goes to infinity of a sub n, which is less than or equal to, nope, not absolute value in the middle, just that, which is less than or equal to the limit as n goes to infinity of absolute value of a sub n. Both of these are 0 from our assumption up above. And negative 0 doesn't really make sense, so positive 0. So this equals squeeze theorem. And we could see something like that happening up here. If the limit was 0 here, I'm going to do like a simulated one up here. That's like having them do this. along the top. And maybe on the other ones doing this, the evens doing this. These are both converging to 0. This limit's converging to 0. This limit's converging to 0. So the limit in the long run for both of them has got to be the 0. That's the idea there. And that's it for 9.1. Peace.